Welcome to the Fundamental Theorem of Calculus Part 1 podcast. All right, so we're going to be evaluating the integral here. All right, so to integrate, I'm going to divide that into two separate integrals. So we have from 3 to negative 1, x cubed dx, and then we have, again, from 3 to negative 1, 1 dx. All right, so integrating it, we're going to increase that exponent by 1. This would be x to the fourth, and divide by the same thing, and we're evaluating that on 3 to negative 1. And then we have, and actually I'm going to write the limits at the end. I'm just going to put one set of the limits of integration on the whole thing. And then integrate this, we increase the exponent by 1, divide by the same thing, that'll become an x. Right? And so we're integrating that and evaluating that from negative 1 to 3. So I'm going to plug the 3 into both terms and then the negative 1 into both terms and take the difference. So this would be 3 to the fourth divided by 4 plus 3. We'll take that and subtract from that what we get for negative 1 to the raised to the fourth power divided by 4 plus negative 1. All right, so 3 to the fourth power is going to be 81 fourths. I'm going to change that 3, so that's going to be 12 fourths. Over here, we're going to have a negative 1 fourth, and that's a negative 4 fourths. All right, so that's going to become 93 fourths minus a negative 5 fourths. So those two negatives are going to become a plus. So that's going to be 98 fourths, which would reduce. Both those are divisible by 2, so that's 49 halves. And that would be the area under the curve from negative 1 to 3. And it's the area under x cubed. All right, so there we integrated and evaluated. Right? And it'd be the same value we would get if we took the limit of the Riemann sums. And this one appears twice. All right, so how about this one? We're going to find the area of one hump of the sine wave. Interestingly, if we took the two of them, they're going to cancel each other out. But let's just take the one hump. All right, so we are going to integrate sine x dx. Okay, the function whose derivative is sine x, that's negative cosine x. So we have negative cosine x, and we're evaluating that from 0 to pi. All right, so we're going to have negative cosine pi minus a negative cosine 0. Cosine pi is going to be negative 1. So that's going to be minus a negative 1. So that's, I'll write in there, minus a negative 1. But that's going to be a plus 1. And then minus, all right, so cosine 0 is 1. So now we've got minus a negative. That's going to be plus 1. So this becomes a positive, and our answer is 2. That's the area under the sine wave. It's 2. Nothing with a pi. It's exactly 2, interestingly enough. All right, so we're going to integrate and evaluate this one. All right, and I'm going to break that into 2, and I'm going to rewrite that negative 6 cube root of x as an exponent, not a radical. Rewrite both of these. All right, so we have x to the 2/3 dx from 8 to 27, and then minus 6x to the 1/3, and that again would be 27 to 8 to 27 dx. All right, so we increase the exponent by 1. 2/3 plus 3/3 is going to give us 5/3. So I have x to the 5/3 that we're going to divide by the same thing. And again, I'm going to just put the limits on the whole thing. And then minus, increase 1/3 plus 3/3 gives us 4/3. So 6x to the 4/3 divided by 4/3. And all of that is being evaluated from 8 to 27. It's nice that those are perfect cubes. All right, let's simplify this. So this is going to become 3/5, and that's going to be, I'm going to rewrite this in radical form because it'll be easier to plug into. The cube root of x, my cube is missing, is kind of hiding there. So cube root of x raised to the 5th power. And actually, I'm going to write that a little bit nicer. I'm going to put the 3 in the numerator and the 5 in the denominator rather than writing it as a fraction. Let's put it as one fraction there. And then over here we'll have minus, that'll be 3/4. Ugh, boy, that looks terrible. All right, so 3, and then cube root of x to the 4th power, and then the 4 will be in the denominator. Oops, and I lost the 6. All right, just put a times 6 in there. Now it looks like 63. Minus 6 times 3. There we go. All right, we got everybody, yes. And that is from 8 to 27. All right, so we'll plug in the 27, then we'll plug in the 8. So we have, and I'll simplify that there. This would cancel out, so this would become a 3, and that would become a 2. So that's going to be 9 halves. So we have 3, as I'm thinking of the 9 halves. We have 3 times the cube root of 27 raised to the 5th power divided by 5. Okay? And then minus 3 times the cube root of 27 to the 4th power divided by 2. Okay? And then we're going to take all of that and do the same thing, but we're going to plug in 8 instead. So I've got 3, and really it's kind of complicated to pull out these because they're different. If they were the same, it'd be nice to pull those out and just multiply by 1 time. My shadow is blocking. I can't see behind my shadow. So I have 3 times the cube root of 8 over 5, and then minus 3 times the cube root, and that's to the 5th power. We lost the power. Minus 3 times the cube root of 8 to the 4th power over 2. And hopefully I can do this kind of small. I'm just going to do that. All right, so now cube root of 27 is 3. 3 to the 5th power is 243. 243 times 3 is going to give us 729. So this is 729 fifths. I hope everyone's okay with that. And then minus, and now I need to have the same denominator here actually, so I'll do that in the next step. I'm going to have to multiply that by 10, by 2, so that my common denominator is 10. So actually I'm just going to write that now. So that would be 1458. So 1458 tenths. All right, so this is the cube root of 27. That's going to be 3 again. And then 3 to the 4th power is 81. And 81 times 3 is going to be 243. So this would be 243 halves. All right, but we're going to have to multiply both the numerator and denominator by 5 so we can combine those. So that's going to be 1,215, hopefully. All over 10. And if I made a mistake, tell me tomorrow. Minus, all right, so the cube root of 8 is 2. And 2 to the 5th power is 32. And 32 times 3 is going to be 96. So this is 96 fifths. Again, we're going to have to multiply that by 2, so we have 10 as a denominator. All right, so that's going to be 192. So 192 tenths And then cube root, that's going to be 2 to the 4th power is going to be 1648 halves. And times 5 is going to be 240. The computation here takes longer. All right, so 1458, and you know, I'm going to wander over and grab a calculator because I'm tired of doing all of these in my head. It's going to be like 200, actually I'm just going to do this one in my head, 243, now that I'm walking with the calculator, 243, wasn't that difficult. Tenths minus, and that's actually going to be a negative here, we're going to have 40 plus another 8, 48, so it's going to be plus 48 tenths. Right, because I'm going to be subtracting a negative. The 240 is greater. So that's going to give us 291 tenths. Or since this is, it would be exactly 29.1. Whew. That was a lot of work, but all the work was the computation. Right? Be careful on your computation. Right? All right, so you can let me know if you have questions in class on this one. Let's go on to the next one. Find the area, and this is a nice simple one, find the area under the curve, y equals cosine x, over the interval 0 to pi halves. All right, so that means we're going to integrate cosine x and evaluate from 0 to pi halves. All right, so dx, don't forget your dx there. So integrating cosine x, that would be sine x. And we're going to evaluate it from 0 to pi halves. So we have sine pi halves minus sine 0. Nice, easy one, easy computation. That's going to be 1 minus 0. I think we can handle that. So 1, that's the amount of area under the cosine curve from 0 to pi halves. That was a nice, easy one. It's nice to have an easy one after one that's a little bit more difficult to computate. This is not going to be a substitution, a U to U substitution. Instead, we have one term in the denominator we should simplify. So we're going to divide everybody. I'm going to rewrite that 1x to the square root of x there as x to the 1/2 plus x minus 2x to the 4th. Divide everybody by x squared, and I'm going to do them all as separate integrals. So this would be x to the negative 3/2 from 1 to 4 dx, plus this would be x to the negative 1, or 1 over x. And I think I'm just going to write it as 1 over x dx. And then 2x to the 4th, negative 2x to the 4th, divided by x squared is going to be 2x squared. All right? So 2 are power rules and 1 is not. All right, so we have a negative 3/2. If we add 1 to it, that's going to be a negative 1/2. So we have x, and again, I'm going to put the limits of integration at the end. X to the negative 1/2 divided by negative 1/2 plus integral for 1 over x, that's natural log of x. And then minus, that would be 2x cubed divided by 3. And all of that gets evaluated from 1 to 4. Let's simplify this. So this is going to be negative 2 is going to be in the numerator, and the square root of x is going to be in the denominator. And then we have natural log of x, and then 2x cubed over 3. I don't know what it is about this side of the board right now. It does not want to write. All right, we're going to evaluate that from 4 to 1. All right, so we're going to put the 4's in for everybody and then the 1's in. I find that easier than doing 4's and 1's for each term. All right, so I've got negative 2 square root of 4 plus natural log of 4. I don't really need the absolute value bars in there. Minus 2 times 4 cubed divided by 3, and all of that, we're going to subtract negative 2 square roots of 1 plus natural log of 1, and I still left the absolute value bars in there, and 2 times 1 cubed divided by 3. All right, so this actually is a pretty easy computation. Negative 2 divided by, that's going to be this, square root of 4 is 2. That's going to be negative 1. So negative 1, I've got this natural log of 4 I really can't do anything with. This is going to be, 4 cubed is going to be 64. And then times 2 is going to be, that's going to be negative 1/28. Right? So then we've got, subtracting, negative 2 divided by the square root of 1 is going to be negative 2, plus natural log of 1, what would I have to raise? E2 to get 1. That's just going to be 0. And then that's going to be minus 2/3. So let's just make everybody thirds so I can combine it together, with the exception of the natural log of 4, who's just going to stay what he is. So we have negative 3/3 minus 128 thirds, and I'm just going to put plus a natural log of 4 at the end. Minus, and this is actually going to be a minus a negative here, so that's going to be a 6/3. So negative 6/3 minus 2/3. So I'm going to extend the page again. So I've got negative 1/3, oh, plus a natural log of 4. Right, all I did was move them over. So we have negative 1/31 plus 8/3, because that's going to be a positive, plus natural log of 4. So that's going to be, my final answer is going to be negative 1/23 plus natural log of 4. We'll just leave it as the exact answer. There we go. So natural log of 4 is certainly a lot less than negative 123. So that's telling me we have a lot more under the radical than under the x-axis than we did over the x-axis. All right, so hopefully that's nice and clear. Some of these, the computation's a little slow. This one really wasn't all that complicated, just took up some space. All right, some properties of integrals. So let f of x dx from a to b be 3, and f of x dx from a to c be 5. We want to find these things here. So number 1, f of x from b to a instead. Right? If you switch the limits, you just negate it. Right? So number 1 here, and I think this is in your notes, f of x dx from b to a is just the negative, and you should write this part in. It shows that you understand the properties rather than just getting lucky and guessing it. F of x dx, so that's going to be a negative 3. Number 2, I'll switch colors so they don't blend together. All right, so we have f of x dx from b to b. Well, if your limits of integration are the same, it's just going to be 0. There's no width, right? So when the limits match, it's always going to equal 0 no matter what. All right, and then number 3, we have f of x dx, the integral of f of x dx, evaluated from b to c. So we have from a to b and from a to c. So to find from b to c, we're just going to take from a to c, which is the whole interval there, and subtract a to b. All right, so that's going to leave us b to c. And that is a to b, f of x dx. So that's going to give us 5 minus 3, so that would be 2. And that's what f of x, the integral from b to c of f of x dx would be. All right, so you can just take the whole interval and subtract off the piece you don't need to give you the leftovers there. And then lastly, we're looking for from b to c. You know that we just did? Do we have the same thing twice? Oh, I'm sorry, it's from C to B. I looked at it backwards. All right, so C to B, or maybe I looked at the wrong one. So from C to B, f of x dx is just going to be the negative of B to C, f of x dx. So that's going to be a -2 instead of a +2. Okay? So pause the screen if you need to and write these down in your notes. That'll help remind you of the rules. And these are very important rules. All right, so let's continue on. I think I've got some more properties. All right, so we're given that f of x dx from 2 to -5 is 14. And g of x dx from -5 to 2 is -5. We want to determine the value, so we have two problems here. Determine the value of from -5 to 2 of 2 f of x minus 10 g of x. All right, so first of all, we make sure the integrals match, and only one of them does not match, and that's this one here, right? But we can change that pretty easily. All right, so for number 2 here, oops, let me write that again. Number 2, f of x dx from -5 to 2 is just the negative of f of x dx from 2 to -5. So that would be -14. Okay? So now our interval matches. So this is just going to be, so 2 times, I can pull the 2 out, f of x dx, and then it's just going to be what we get for, and again I can pull the 10 out, 10 times the integral of g of x. This is from -5 to 2. All right, so that's going to give us 2 times -14 minus 10 times -5, which is -28 plus 50, or 22. Right? So it's just using our properties here. Right? And then the last one here, given that f of x dx from -1 to 7 is 4, and 7 to -1 g of x is -2, we want the value from 7 to -1. So g of x matches, f of x doesn't right now. So f of x, 7, we want -1 to 7, or 7 to -1. All right, so that would be equal to, notice I just switched the opposite of -1 to 7 of f of x dx, so that's just going to be -4. So this is going to be, I can pull the 1/2 out. Boy, these are starting to blend together. So let's pull the 1/2 out, f of x plus, oh, dx. Squeeze my oops, well, I need some more space anyway, I'm tired of bending over to write dx plus, and then it would be, what was it, 4 times g of x dx from 7 to -1, and the only thing I don't know is I don't remember what the numbers were. So it was -2 and -4. So that's going to give us 1/2 -4 plus 4 times -2. So that's going to give us -2 plus a -8, or a -10. So this is just using those properties, knowing that as long as those intervals match, you can add and subtract our definite integrals. All right? All right, we have a little bit more time. Let's see if we can do another problem. All right, so here we have a couple more, just the properties. I think this is going to be the last page I do, and then we'll look at definite, and tomorrow in class, definite integral involving absolute value, because that's very important to know how to do. All right, so here we have f of x dx evaluated from 0 to 1 is 1. F of x dx from 0 to 2 is 4. And f of x dx from 1 to 4 is 7. Notice that 0 to 1 and 1 to 4 match up. And 0 to 2 is just kind of in between those overlaps. All right, so the first one is finding the integral of f of x dx from 0 to 4. All right, so notice we're going to add the 0 to 1 with the 1 to 4. And actually I have this written down. So all I'm going to do is, move the screen so you can see it. I think it's very interesting. I think all you see is what I see. Oops. So even though it's on the computer already, I don't think you see it until I move the screen. Oops, well, I moved two of them down. That's right. So f of x, there's f of x dx, that's too far now, from 0 to 4 would just be from 0 to 1 plus 1 to 4. So that's going to be 1 plus 7 or 8. And the second one there is from 1 to 2. So 0 to 2, if we subtract out the 0 to 1, we're going to be from 1 to 2. And that's the area in between. All right, so f of x dx from 1 to 2 is just 0 to 2 minus 0 to 1. So it's going to give us 4 minus 1 or 3. Here we have f of x dx from 4 to 1. That's just going to be the opposite of 1 to 4, and so that's just going to be a negative 7. And finally, we have f of x dx from 2 to 4. So we're going to go from 0 to 4 and subtract out 0 to 1. So we're going to have the 7, which is f of x dx from 1 to 4, plus the f of x. I should have written them in the reverse order. I should have 0 to 1 first, because it goes 0 to 1, then 1 to 4. So that gives us 0 to 4. And we don't want 0 to 4. We want 2 to 4. So we'll subtract out 0 to 2. So that's going to be 7 plus 1 minus the 4 for 0 to 2. And that gives us an area of 4. All right, so I think a lot of this was review, and I think it was pretty straightforward, but ask me in class if you have any questions. And I am under my 30 minutes, and I'm going to end this podcast. All right, bye.